Our next presenter is Dustin Abele. Dustin is a doctoral student in chemistry. His presentation is entitled Sustainable Materials for High Energy Density Lithium-Ion Batteries. Dustin?
Demand for lithium-ion batteries is rapidly increasing, and it's expected to dramatically increase from now until the year 2030 and beyond, with a kind of a quintupling expected. Currently, we use in the anode graphite. Graphite is either mined or can be synthesized from petroleum or coal products, which are both kind of terrible for the environment. So while lithium-ion batteries in general, you think of trying to be a renewable energy source to store that energy, using kind of dirty products to make those batteries does not really make sense. Fortunately, we have a couple of other options on our hands, and the graph in the top middle actually show a variety of different chemistries that lithium-ion batteries are using. And just to pull focus to the very bottom of the green is sulfur chemistry, and then the top is silicon. So silicon is made from sand, and it has the benefit of also being the lowest weight and the smallest size. So that gives you the highest energy density in both a volumetric and a gravimetric sense, which is kind of ideal in what we want. So my research is really focused on pushing silicon chemistries forward. So on the bottom here, I show a synthesis that I've developed in my lab for my dissertation research using sustainable materials that are also very affordable. So aluminum chloride and sodium chloride. And thankfully, when you mix those two materials together, we can get them to melt at relatively low temperatures, 110 degrees Celsius, which is pretty low in the chemistry world. We can add magnesium silicide to this reaction to make silicon particles. These silicon particles can then be used for lithium-ion batteries, and this whole process is done in one step, so it's fairly simple. On the right-hand side, I've taken these silicon particles and I've made batteries out of them myself in the lab. So I make can-made batteries. It's kind of difficult to do and tedious, but we can do it. So the top I am showing here is the capacity of the batteries that I've made, top right. These batteries are then cycled time and time again, kind of like you would cycle a battery in your cell phone, so it goes down to 0%. We bring it back up to 100%, back down to 0, over and over and over again. And we can plot out the capacity for each cycle as we measure it. You'll notice there's a kind of a grouping at the top here above 500 that seems like the best candidates, but they quickly fade over the course of 100 cycles, and before you know it, in the battery world, they'll be dead. But you notice there's these, the black triangles is a different batch that we made, and it's actually flat all the way across. Slightly lower capacity, but interesting nonetheless. What we can do is we can actually look at the efficiency of the electron transfer from cycle to cycle of these batteries, and that's when we actually notice something different between the two. The group at the top that faded quickly is showing this weird plateau in the bottom graph for the first 20 cycles, and then continues on upward towards 99%, while the ones in the black triangles do not. They quickly get up to 99% efficiency of electron transfer, and we've actually found something interesting here, kind of a new novel way to make a silicon material not used before.
Thank you, Dustin.